Alright, so a block of mass 4.0 kg causes the spiral spring to extend by 0.16 meters from its unstretched position. The block is removed, and another body of mass 0.5 kg is hung from the same spiral spring. If the spring is then stretched and released, what is the angular frequency of the subsequent motion? Right. So by looking at what we have here, we have m initially as 4.0 for the first scenario, and then we have x, or change in x, as 0.116. All right. So this is modeling a system where a mass is hung. So that mass is hung and then is allowed to go, the weight of the mass is making it go up and down, right? So the formula for the restoring force is F is equal to kx, where the F is the mass of the object, and is the weight of the object rather, right? So the F is the weight, right? So that means we're going to have F, which is 4.0 times 10, that's mg, mass times acceleration due to gravity, is equal to the force constant times x, which is the extension, right? So times x, which is the extension. I can just replace that with 0.16. So I can replace that with 0.16, such that k will now equal 40 divided by 0.16, which is 250. So this is 250 Newton per meter. So now we have our force constant for the string, right? So that we can now come back and answer the question for angular frequency. Now, angular frequency given by W, angular frequency given by W is equal to 2 pi over period. But then period is given by 2 pi square root of m over k. So there are a lot of formulas involved, right? So t is equal to 2 pi root m over k. That means that t is equal to 2 pi times the square root of, now for the actual question, we are considering when the mass is 0.5 over the force constant is, we've calculated that to be 250. So I can come back and substitute here into my formula for angular frequency, such that W would now be equal to 2 pi over 2 pi root 0.5 over 250. 2 pi cancels out 2 pi, such that W is now just the reciprocal of what we have under the square root sign, which we can just rewrite as W is equal to square root of 250 over 2 pi over 0.5, sorry, my bad. So 250 over 0.5, right? Because the 2 pi is cancelled out, so we just have 1 over all of that, and then we have this here. Divide that, we have that as root 500, of which 100 is a factor, so we can just rewrite that as 10 root 5. Okay, so 10 root 5 rads per second. The option is option D. So again, the process is quite, interesting, right? The first thing we needed is, that at the end of the day, we had to use this formula. So that means that we had to have found our force constant. So we went back to the first scenario that was given to us, and then we used the Hooke's law. This is actually Hooke's law, right? So we use Hooke's law to find the force constant, and we're able to plug that in and solve all the way down. Now, two things that are very important in questions like this is that as many equations as possible. right? You know as many equations as possible, and then also that your algebra is sound, right? So if you know as many equations as possible, because this question really is not under elasticity, but then Hooke's law came into play. Okay, that's question 1. Let's take question 2. It's a body timed 20 oscillations of a certain pendulum 3 times and obtained 44.3 seconds, 45.5 seconds, and 45.7 seconds. Calculate the mean period of the oscillation of the pendulum. Okay, so it was 20 oscillations, and each time the 20 oscillations gave something different. Okay, so the first thing we need to do is we need to calculate the mean of the 3 of them. All right, so we need to calculate the mean for 20 oscillations, which would just be 44.3 plus 45.5 plus 45.7 over 3. The first thing we'll do is we calculate the mean, and that's going to give us 45.5 plus 45.7. That gives 135.5, which we can now divide by 3 to give us 45.1667. So the mean for a single oscillation which is basically a period is the time for one oscillation, right? Now we have the mean for 20. We now have to calculate for 1, right? So that would just be the answer we got, 45.1667 divided by 20. So that would be 2.26. That's 2.26 seconds. All right, so that's the answer, 2.26 seconds. Okay, so that's question 2. So question 3 says, a loaded spring is set in simple harmonic motion. The force that tends to restore the load to the equilibrium is the restoring force. That's what we are being asked. We're asked, what is the restoring force? So there are 2 major systems for simple harmonic motion. We have the mass spring, and then we have the pendulum. So in the mass spring, what happens is that there is a mass attached to a spring, okay, and then that mass is initially pushed or pulled, all right, and because of that it begins to go back and forth and back and forth, and that's the simple harmonic motion system. All right, it goes far beyond the starting point, and then to now go, but when it's being restored, when it's coming back, to push far beyond, the equilibrium, the middle point that it was before, go to the other end, then to be pulled back again, and so on and so forth. So what is doing that restoring? When it goes to one end, what pulls it back again to the middle? All right, that is the spring. All right, it's the force on the spring that does that job, and the mass spring system. All right, this question is actually for a mass spring system. So is elastic is the elastic force, all right, given by F is equal to kx, that does that, that job of pulling it, back and forth and back and forth. Now, for a pendulum, so if this question had said a pendulum is set in motion, for instance, right? So for a pendulum, what restores it is the gravitational force on the weight. So there's a string, all right, and you push it this way. So what happens is that your string begins to go back and forth and back and forth and back and forth. So when it's here, what pulls it back down, what drags it to come down again is the weight. right, is the weight of the object that is swinging, that pulls it back, and then when it gets jointed, it pulls it back. So in summary, for a mass spring system, restoring force is elastic force. Pendulum restoring force is gravity bracket the weight. Right here it's F is equal to kx, like I said, but here it is F is equal to mg, or W is equal to mg. Okay, so now we know the restoring force for both systems. Okay, question 4. A loaded spring performs simple harmonic motion with an amplitude of 5 cm if the maximum acceleration of the load is 20 cm per second. Calculate the angular frequency of the motion. Okay, so our formula for angular frequency is given by or let's take the formula for angular acceleration, a maximum acceleration rather. The formula for acceleration is given by W squared A, where small a is our acceleration maximum, capital A is our amplitude, and then omega is our angular frequency. So I have A as 20 cm, so I'm plugging into this formula, right? A as 20 cm per second squared is equal to omega squared times my amplitude of 5 cm. All right, now I'm not bothered with the unit because you can see cm, so I divide both sides. I'll have omega is equal to 4. Omega squared rather is equal to 4. So omega would be square root of 4, which is 2. All right, omega is 2. The answer is B, 2 rads per second, 2 radians per second. Okay. A pendulum bulb executing simple harmonic motion has 2 cm and 12 Hz as amplitude and frequency respectively. Calculate the period of the motion. All right, so period is there are two formulas for period. The first one is that period T is equal to 1 over F, and the second one is that period T is equal to 2 pi root m over k. Oh, there's a third one actually. So this one is for a mass spring system. The third one is that T is equal to 2 pi root L over G. Right, this one is for a simple pendulum. You need to know all three formulas. But if you look at this, I mean, this just, it's just this first formula, right? So it's just going to be period T is equal to 1 over 12, which would give you 1 over 12 will give you 0.083 seconds. That's option B. All right. That's option B. Question 6. A simple pendulum makes 50 oscillations in 1 minute. What is the period of the oscillation? So period, we need to define period. Period T, right? T is the amount of time for only one oscillation. Only one oscillation. Very important, just one. So once you have it this way, it's easy for you to know what you're supposed to do. All right, and it's in seconds, right? So the unit is in seconds. So 50 oscillations in 60 minutes, in 60 seconds, right? So how many seconds will it take for one oscillation? So for one oscillation, it's going to be time, that's 60 seconds over 50. So how long did it take for 1? All right, so that would be 60 divided by 50 gives you 1.2 seconds. The correct answer is that's question 6. Question 7. The student found out from a simple pendulum experiment that 20 oscillations were completed in 38 seconds was the period of oscillation of the pendulum. All right, so period, what does period mean? We are asked to find period. Period is the time taken, amount of time taken for just one complete oscillation. Time taken for one oscillation. So my period is going to be, in this question, I mean, we have 20 oscillation in 38 seconds. So for one oscillation, all right, the time is going to be 38 seconds divided by 20 to know how long it took for just one, all right, which would give you about 1.9 seconds, all right? So it takes 1.9 seconds on the average for each oscillation. That's D. All right, question 8. A simple pendulum between the rest position and the maximum displacement possesses, right? So the correct answer for this is that between the rest position and the maximum displacement, it possesses both kinetic and potential energy. And here's why. So the law of conservation of energy applies to your simple harmonic motion. You know, I mean, we consider them to be ideal systems, right? So when we are doing all of our calculation and all of that, we assume that there is no loss of energy, right? There's no friction, you know, it's a perfect utopia, right? So we don't have any of those. And so because of that, here's what's going on. There's a simulation on the side that you probably would want to also explore, just to, you know, help you hold on to this a bit more. So they are basically, well, okay, let me make it more positions, right? Okay, so now we have 5 positions, right? We have 2 extremes, 1 in the middle, all right, and then, you know, 2 right in between. Now, this is the position of maximum displacement. Here too, this position of maximum displacement. And this position here in the middle, you can call it your equilibrium or rest. So, in a sense, right, it's like this is where the ball or whatever is in the, you know, undergoing the motion always wants to rest at. So when it swings all the way to the end, you know, even as it's swinging, it's already reducing speed because it's trying to come back here, right? And then when it picks up from here, it begins to increase speed as it comes back, okay, accelerating backwards, trying to get here. So the goal of it is to get here. So we'll call this position our equilibrium or rest position. Okay, so the 2 systems or the two forms of energy that are at work here is we have the gravitational potential energy, all right, and the kinetic energy. If you know your formulas, you know that your gravitational potential energy actually depends on height, all right? The formula is mgh. And your kinetic energy depends on what? Velocity, half mv squared. So at the maximum displacement, here's what you will notice. You would notice that the velocity is 0 because it actually stops. So your object would move but reducing speed, get here and stop completely before it now starts, you know, tracking back, and then it now begins to pick up speed again. So what happens here is that your kinetic energy is 0 and your potential energy will be maximum. The reason why is that you have the highest displacement height, at the highest height at this point. So the same thing applies here. Your kinetic energy is 0 because it's also going to stop there and start tracking back. But then you have the highest potential energy. Again, because the displacement, the height is maximum. Now at this point here, what happens here is that this is the base position. So the displacement is 0, the height is 0. So you actually have what? zero potential energy. But then if you think about it, this is where it is fastest, because it sweeps past that position, right? Like very fast. So like it just, because it's trying to get there, so it loses up a lot of energy and it just moves back past that position. So in a sense, at this position here, your velocity is maximum, all right? And what comes along with maximum velocity, kinetic energy, is also maximum. So we've established that at the middle here, the rest, potential energy is zero because there's zero displacement, and kinetic energy is maximum. We've also established that at the end points, all right, kinetic energy is zero because the object literally stops, all right, so there's no velocity, but potential energy is now maximum because of the high displacement. So what happens here? Well, because we are being asked for between the rest position and the maximum displacement. So our point of focus, right, is actually here and here. And what you see happening here? What is happening here is that, oh, you have some height and you still have some velocity. So at that point, you have both kinetic and potential energy, some of it. All right? You have some of it at those points. But by the time you get to the middle, the potential energy is finished, your kinetic energy is maximum. By the time so that's just the, and by the time you get to the end point, your potential energy is maximum, your kinetic energy is zero, and then it just keeps going. I would really recommend that you play around with the simulation that is on the platform. That would really help your understanding of this, right? So the correct option is option A. Okay. So this says an oscillating pendulum has a velocity of 2 meters per second at the equilibrium position. All right, so here's our equilibrium position. That means that we are told that V is 2 meters per second and 0 meters per second velocity at point P. All right, so this is our maximum displacement, right? So you'd expect that velocity will be 0. Good. So we're asked to calculate the height, all right, the actual displacement. So it's going to be a great idea if you just keep back to the question before this one, so you have a very good understanding of what I'm going to try to explain very quickly. At this endpoint here, we have maximum displacement, which of course maximum height above the rest position, right? Which means that your gravitational potential energy is max. And at this point here, we have maximum velocity, right? So your speed is highest here. So at this point, your kinetic energy is equal to maximum, all right? So what happens is that due to the law of conservation of energy, the maximum potential energy is equal to the maximum kinetic energy. So we have, I can say GPE max is equal to KE max, all right? This KE max occurs at the equilibrium or rest position, while the GPE max occurs at the endpoints, the points of maximum displacement. What is the formula for GPE, gravitational potential energy? That is mgh. We can say mgh must be equal to half mv squared. Right, so looking at this closely, you would see that we can actually cancel out what? The masses on both sides, which means that this relationship really has nothing to do with the mass of the objects involved, right? And we can now plug in what variables do we have? We have our velocity as 2.0, and we have our gravity, acceleration due to gravity as 10 meters per second squared. So I'll plug this in and solve for V. So I'm going to have G times 10 is equal to 1 over 2 times the velocity squared times 2 squared. Oh, I'm sorry. This should be h times 10, right? Yes, if you plug in properly. So, or 10 times h. So basically 10h. Good. So on this side, this would be 1 over 2 times 4 is equal to 10h. So 10h is equal to 2. That would mean that h would be equal to 2 over 10. H is equal to 0.2 meters. All right, h is equal to 0.2 meters. So how did we solve this question? We solved this question by understanding that at the middle, we're going to have maximum kinetic energy, and at the end point, we're going to have maximum gravitational potential energy. And due to the law of conservation of energy, they must be equal, all right? Because the total amount of energy in the system must be constant. So we equated it and found out that, we could cancel out the masses, which we did. And then, it was now an easy right from there to solve to the value for H. All right. So question 10 says, during the training session, two footballers pass the ball repeatedly between each other. The to and from movement of the ball is not simple harmonic because all right, so let's look at this. So two players are kicking the ball between themselves. I draw terribly, so just, bear with me. So player 1 and player 2, and then they kick the ball, between themselves, and then the ball just keeps on going back and forth, right? Back and forth. So that's the best illustration. So we can use this and see. Okay, acceleration of the ball is not directed towards a fixed point. That is very true. All right. So it's not a system that the acceleration is directed towards a fixed point. There's no restoring force, as it were. All right. The restoring force is just them kicking the ball back to each other. So there's nothing pulling it to a middle point. All right. So that already discounts both 1 and 2. And then the acceleration of the ball is not directly proportional to the displacement from a fixed point. That's also true. All right. Because again, they receive the acceleration from where, they kick the ball, right? And it's not directed towards any point at all. It's just, it's just a to and from motion, right, of kicking the ball. So it's not, on all 3 counts, it fails to be referred to as a system of simple harmonic motion. All right, so question 11. The amplitude of a particle executing simple harmonic motion is 5 cm, while its angular velocity is 10 rads per second. Calculate the magnitude of the maximum acceleration of the particle. Calculate the magnitude of the maximum acceleration of the particle. Okay, so our formula is A is equal to omega squared A. All right, so capital A. So small a represents maximum acceleration. Omega is your angular velocity, sometimes referred to as angular frequency, and A is your amplitude. So we can just substitute, right? We have A, which is what you're looking for, is going to be equal to omega squared. That'll be 10 squared times your amplitude, which is 5. All right, so that's 5. But if you look at it closely, your units here are in meter per second squared. That means we have an issue here, right? So I need to rewrite this as, I'm going to convert 5 cm to meters. That would be 5 out of 100. So at the end of the day, A will just be equal to 5 meters per second squared. Right, so it's really important that you look out for your units. 100 cm makes a meter, right? So it's as simple as that. Okay, question 12. The amplitude of the motion of a body performing simple harmonic motion decreases with time because the correct answer is A. Frictional forces dissipate the energy of the motion. All right, and you see this everywhere. If you have anything that is just going back and forth and there's nothing that is keeping it, to continue in that motion, you find out that over time, it's just come back to, it will just keep on reducing, the displacement from the center will keep on reducing until it comes to a point where it just stays, right? So, and that's due to frictional forces that are present in an ideal system. Although for the system that we discuss usually and we do calculations on, all right, for the systems that we discuss and we do calculation on, we assume that friction is 0. For the mass spring system and for the simple pendulum systems. The bulb of a simple pendulum takes 0.25 seconds to swing from its equilibrium position to one extreme end. Calculate its period. Okay, so we need to draw this out and really think about it, right? So this is the bulb here, and you're being told that it takes 0.25 seconds to swing from here over here. 0.25 seconds to swing all the way there. All right, so that means that for it to complete one oscillation, it has to swing from here over here. All right, swing back here. So this is the first time is doing this kind of motion. The second time is doing this kind of motion. It also has to swing to the other end point. That's the third time. And then swing back here, because it's one complete oscillation. It has to end up where it started out, right? So it's four. It has to go from, do the first one, going from the center to the end point, then go back from the end point to the center 2, from the center again to the other end point 3, and then from the end point back to the center 4. So it's 4 times, all right? So it's going to be 4 times. So if this was 0.25, and we are considering a frictionless system, that means that, you know, the time it takes will just remain constant. So that will be 4 times 0.25 to give you 1 second. So it's going to take 1 second to go to complete the journey back to its starting point. Okay, that's 14. 15 says, the bulb of a single pendulum takes 8 seconds to complete 10 oscillations. Determine the frequency. All right, so frequency is, the definition of frequency itself is, answers the question, how many oscillations per second? How many oscillations per second? So there are 10 oscillations in 8 seconds. So in 1 second, you have to divide that 10 oscillations by 8 seconds to know how many oscillations you have in each second, right? If you divide that, that gives you 5 out of 4, which should give you 1.25 rather. So 1.25 hertz. All right, so the idea of the unit of hertz is actually just per second. All right, it's just per second. That's option C. All right, question 16 says, the diagram below shows the position of a single pendulum set in motion. At which positions do the pendulum have maximum kinetic energy? All right, so maximum kinetic energy. We solved this a while back. I think it was question 9, like where we actually took time to explain. So if you want to, you can go back there and watch it. But I'll just do a quick one again. So when you consider the motion of a simple pendulum, right, there are 2 endpoints here and here. And at these 2 endpoints, if you think about it and understand the way it moves, it actually stops. All right, the motion actually totally stops at this point. So it goes up to the end, stops, then picks up, and then starts coming back again, right? So at this point, your velocity is 0, which means, of course, your kinetic energy would also be 0. Why? Because, I mean, and I expect you know this now, your kinetic energy formula is half mv squared, and your potential energy formula is mgh. Okay, so if you don't know this, right, then that means that you have some issues that you probably need to take time to deal with in terms of going back to learn some of the foundational topics and formulas and all of that. And that's not a problem. It just means that you have to, and because physics also builds, so you need to just be very careful about, you know, and try to stack up on as much information as you would need to. Anyway, so your kinetic energy here is 0 because your velocity is 0, but then your potential energy is maximum. Why? Because your height above, you know, the equilibrium position is highest, and potential energy actually depends on height, right? So here you have maximum potential energy. But then at the middle here, all right, what you have is, you have your potential energy as 0. Again, why is my potential energy 0? Because your height above this point is 0. You are at that point, right? So your potential energy is 0, but your kinetic energy is maximum. And why is your kinetic energy maximum? Because of course it depends on velocity, right? And you know, you're just this at this point is 0, then it begins to move and it gets fastest here. Remember, the acceleration is always directed towards the center, the fixed point. All right, so that's where it's fastest. So the correct answer to this question is 3. All right, at position 3. Okay, so let's move on to 17. 17 says the frequency of a swinging pendulum is this is a definition, right? Basic definition is the number of complete oscillation the pendulum makes in a second, right? So how many oscillations do you make per second? All right, how many complete oscillations do you make in a second? So it is the reciprocal of a period. All right. 18. The length of a single pendulum is increased by a factor of 4. By what factor is its period increased? Very, very important question. The length of a single pendulum is increased by a factor of 4. By what factor is its period increased? So if you think about it, right? This formula, there are 3 formulas for period. The first formula is T is equal to 1 over F. The second formula is T is equal to 2 pi. The second formula is T is equal to 2 pi root L over G. This is the one that applies to simple pendulum. This is one that applies to simple pendulum. And the third formula is T is equal to 2 pi square root of M over K. Okay, so we have these 3 formulas, and then this one is for the mass spring system. All right, so your mass spring system depends on, your period depends on your mass and your spring constant. All right, but we are dealing with a simple pendulum system, and it depends on what? The length of the string and the acceleration due to gravity. All right, so let's look at both systems. So initially, the initial scenario, you had 2 pi and then square root of L over G. Okay, so the length was as it was. All right, and then the second scenario, watch closely, it now becomes 2 pi square root of 4L over G. So what we're going to try to do is I'm going to try to see if I can find out the relationship between T2 and T1. All right, it's a very neat method. All right, so just track with me. I'll just take this and write it up here. T2 is equal to 2 pi square root of 4L over G. So I can write this as T2 is equal to 2 pi times root 4 times square root of L over G. So I can write this as T2 is equal to 2 times 2 pi square root of L over G. Because root 4 is 2. So in a sense, I'm saying that T2 is equal to 2 times of T1. So the correct answer is B, because it's saying that if you increase the length by a factor of 4, then the pendulum, the period is increased by a factor of 2. Right, so you probably want to try this out yourself, right? It's a very neat trick, and this is not just a formula, a question about simple pendulums and stuff, right? But it's about learning how to manipulate formulas, because this question could come up with anything. It's actually a variation problem, all right? So it could come up in practically every single formula that exists in physics. They could give you a question like this. So it's not just getting the answer, is about understanding the method. So you want to practice this, to ensure that you can actually relate to everything that was done here. All right, that's question 18. Question 19. The mass on a loaded spring oscillates vertically between 2 extreme positions. All right, so I'm going to try to describe this, what it looks like. There's a simulation on the platform that actually does, a good job on this. On this actually. So what you have is there's a spring that you attach a mass to, right? And then that mass has a weight, all right? And what you do is you pull the mass down. You can pull it down and leave it. And because of the elastic nature of the spring, it begins to go up and down, up and down. All right, so it's going to have two extreme points. It's going to have an extreme point here. That's when, so at this point the string will be compressed, and it's going to have another extreme point here. All right, at that point the spring would be stretched. All right, so again, I would really recommend that you go and you know, walk around the simulation, and so that you get this properly. So what happens is that when it moves up, it actually moves up, and at this point it stops, then starts coming down. So at this point here, at the point of maximum here, it stops, maximum displacement, it stops, and at this point your velocity is 0. Same thing here, at this point here, it stops, right? It stops and then it starts moving back up. So at this point your velocity is also what? 0. But at this point here, it has maximum velocity. So it literally just, you know, increases speeds until it gets to the equilibrium position. But then the moment it passes the equilibrium position, it begins to drop speed. And that happens when it's going up and when it's going down. The same exact thing happens. So, at the same time, the restoring force for the system is the elastic force of the string or the spring, right? Because that's what pulls it, you know, it compresses. When it compresses it, of course, if you compress the spring, it wants to push back, right? So it pushes the mass down. All right, it pushes the mass down and it pushes it beyond the equilibrium position, but then it now becomes stretched. And if you stretch the spring, what happens? It always wants to come back. So it now begins to come back again. So the spring is the one that determines that keeps trying to restore it back to the original point, you know, and keeps making it go, you know, go through that motion. So your elastic potential energy is maximum when it is completely compressed or completely stretched, right? So your elastic potential energy is going to be maximum here. All right, so elastic potential energy will be maximum here. Elastic potential energy will be maximum here. Meanwhile, at this point here, kinetic energy will be maximum. Why is kinetic energy maximum? Because kinetic energy is linked to velocity, half mv squared. So if the velocity is maximum, kinetic energy will be maximum. But for the elastic potential energy, it's actually linked to displacement. All right, the formula for this is F is equal to kx. So let me write both formulas here. Elastic potential energy is equal to E is equal to half kx squared. Sorry, it is the force that is kx. So E is equal to half kx squared. And then your kinetic energy is E is equal to half mv squared. So this is linked to displacement, of which you have maximum displacement at the end point, right? So at point P and point R, you have maximum displacement. However, at point Q, you have 0 displacement but maximum velocity. All right, so let's now read the question. The momentum of the mass is maximum at Q. That is correct, or that is true. All right, why is that true? Because at that point, momentum is equal to mass times velocity. So it's linked to velocity. So if velocity is maximum, momentum would also be maximum. B, the kinetic energy of the mass is maximum at P. That's not true. All right, that's not true. And why is that not true? It's not true because at this end point here, at the end point, your velocity is 0. So your kinetic energy would be 0, right? Again, K is equal to what? Half mv squared. The total energy of the system is always constant. That is very true. Law of conservation of energy is observed in simple harmonic motion systems. And D, the elastic potential energy of the spring is minimal at Q. That is true. All right, is minimal at Q, is maximum at P and R. All right, so if you're not familiar with this system at all, I would advise you to again go on the platform, play around with the pendulum, and then come back and watch this again with the mass spring system rather, and then come back and watch this again. And the system is very similar to that of the simple pendulum. Just in the simple pendulum, the restoring force is the gravitational potential energy. That's all, or force of gravity. That's all. All right. So yeah. So the question is, which of this is not correct? And that correct option is, or that not correct option is B. Right. The kinetic energy of the mass is not maximum at P. It is minimal at P. 20. The motion of a body is simple harmonic if so part of the motion is a straight line, not necessarily. Acceleration is always directed towards a fixed point. True, but not completely true. Acceleration is proportional to the square of the distance from a fixed point. Not true. Acceleration is proportional to the distance from that point. All right, so good. So the correct answer is D. All right, is both directed towards a fixed point and proportional to the distance. So both of these have to be true for it to be a simple harmonic motion. That's D. All right, 21. The period of a simple pendulum X is 5 seconds, was the period of a simple pendulum Y, which makes 50 vibrations, and the same time it takes X to make 20 vibrations. Okay, good. So we have the period of the first one is 5 seconds. So that means that for X, time for one oscillation is 5 seconds. All right. And we are told that the other pendulum makes 50 vibrations, the pendulum Y, right? In the same time, it takes X to make 20 vibrations. So let's find out how long it takes X to make 20 vibrations, right? So time for 20 vibrations or oscillations is going to be 20 times 5. So that means the time that, we are comparing both of them based off of is 100 seconds. All right. So Y makes 50 oscillations or vibrations in 100 seconds. So what is its own period now? So period is how long it takes for one oscillation, right? So the period would just be 100 divided by 50, which is going to be 2 seconds. So that means that it makes 100 vibrations in 2 seconds. I'm sorry, it makes one vibration rather in 2 seconds. The answer is B. The period of an oscillatory motion is defined as the time it takes to complete one oscillation, one single oscillation. 3. The period of oscillation of a particle executing simple harmonic motion is 4 pi seconds. If the amplitude of the oscillation is 3 meters, calculate the maximum speed of the particle. All right. So the formula we use to calculate for the maximum speed is omega times the amplitude. All right, so here we have amplitude as our amplitude is 3.0. For omega, we don't have omega, right? But omega is equal to 2 pi over period. All right, so omega is equal to 2 pi over period. And we have our period as what? 4 pi. So that means that omega would be 2 pi over 4 pi, which should be 1 over 2. All right, 2 pi over 4 pi, which is 1 over 2. Therefore, our maximum speed would be equal to A, which is 3, times what? 1 over 2, which is our omega, which gives us 1.5 meters per second. 1.5 meters per second. All right. So that's for question 23. Let's take on 24. 24 says two simple pendula of A and B, or two simple pendula A and B of equal lengths and of masses 5 grams and 20 grams respectively are located in the same environment. The periods A and B, TA and TB, of their respective oscillations are related by the equation, so we need to find what relates them. All right, so let's take our formulas for period. One formula for period is 1 over F. Another formula for period is 2 pi root m over k, and that formula for period is 2 pi root L over G. Okay, so this one applies to the simple pendulum. This one applies to the mass spring. And of course, this one applies to both. All right? So we are dealing with simple pendulum. And as you can see, in a simple pendulum, the change in mass has nothing to do with the period. The period of the simple pendulum system has nothing to do with the masses. So that means that if the only issue is that if they have equal lengths, which is what really matters for a simple pendulum, then that means that their periods will be the same. The correct answer is option C. All right, the periods will be the same. For a mass spring system, that is where the constant, the force constant, and the mass actually do matter. So if you change the mass for a mass spring system, then the period would change. All right, but for a simple pendulum, it's unless you change the length or the gravity, acceleration due to gravity, that's when you see that change. So it's constant for that particular scenario. Okay, 25 says 2 simple pendula X and Y make 400 and 500 oscillations respectively in equal time. If the period of oscillation of X is 1.5 seconds, what's the period of oscillation? Of Y? Okay, so equal time. So let's find out how long X used, since they both used equal time, and they will now apply the same time to Y. All right. So we'll find out how long X used. So we have that the period is time for one oscillation is 1.5 seconds. So how long will it take for time for 400? Time for 400 oscillations will be 1.5 times 400, which is 600 seconds. All right. So if you think about it, right, there are a lot of questions that are basically just proportions. So you need to be able to, and I would recommend that you take variations when you learn variations seriously, not just to learn the formulas, but try to see if your mind can capture what the relationships should look like. That will really help you in physics. Variations is a topic in math. Okay, so if the period of the oscillation is that, so we've done that, right? So now we know the time. So the time for Y now, the time for 500 oscillations is 600 seconds, because we were told that it happened in equal time. So what is the time for one oscillation? Because that's the definition of a period, right? So that time would be 600 seconds over 500. So we're saying how long does it take to do just one? All right, which gives you 1.2 seconds. That's option C. Okay, that's question 25. 26 says, which of the following graphs correctly represents the relationship between the kinetic energy and the displacement from the point of release of a swinging pendulum ball? Okay, so from the point of release of a swinging pendulum ball. So the way we release the swinging pendulum is that we take it to the side. All right, so if this is a simple pendulum, right? So we take it here, we release from here, and we just allow it to fly, right? So what's the kinetic energy like? All right, what's the kinetic energy, right? So at the starting point, let me draw a graph for the kinetic energy. All right, so KE against the displacement from this point. So at the starting point here, you will know that your velocity is 0 at this point. So your kinetic energy is 0. So you're going to start here. By the time you get to the middle, your kinetic energy is maximum because your velocity is maximum, right? That means you're going to have your kinetic energy would have swollen to somewhere here. And by the time you get to the other end point, your velocity is now 0 again. And your kinetic energy is 0. So you are back here. All right? Because at this time is that by the time you get here, your kinetic energy is back to 0. So you would expect to see a system like this. All right? So something like this would define what the graph would look like. And we have that. That's option C. Option C. All right, 27. Which of the following statements about an object performing simple harmonic motion is correct? A is acceleration is minimal at the extreme ends. Now that's true. So acceleration is directly proportional to displacement, right? So that means that when the displacement is highest, acceleration would always be what? Be highest. All right. So this statement is wrong because it's going to be maximal, right? It's supposed to be maximal at the highest. B is that the acceleration is 0 when it's displaced from the equilibrium position. That's not true. In fact, the acceleration is only 0 at the equilibrium position, all right? Because at that point, your displacement is 0, so your acceleration will also be 0. C is that the acceleration is constant and directed towards a fixed point. That's wrong. Even though the acceleration is directed towards a fixed point, it's not constant. The acceleration is varying linearly, right? It changes. The acceleration is varying linearly with displacement. So it's the correct option is option D. All right, the correct option is option D. Okay, 28. Which of the following statements about simple harmonic motion is correct? The point of acceleration varies linearly as acceleration due to gravity. Linear acceleration is always directed towards any variable point. Wrong. Total mechanical energy is always conserved. That's true. All right. So law of conservation of energy. So the correct option is C. Linear acceleration varies inversely. No. Linear acceleration is directly proportional to the linear acceleration, right? Yes, is the acceleration is directly proportional to the displacement from a particular point, right? And is directed towards that point. So it's not varying inversely. 29. Which of the following statements about the motion of a simple pendulum is true? Okay. It possesses maximum kinetic energy at extreme positions. That's wrong. All right. At extreme positions, it possesses no kinetic energy because your velocity is 0. All right. It swings faster at the poles than at the equator. It's a simple harmonic motion when the angle of displacement is large. It passes the equilibrium position with minimum speed. So the correct answer is B. All right, and that's due to variation of the of G. You know, your period C is equal to 2 pi root L over G. That means that your period actually depends on gravity, right? And so let me put it this way. C is inversely proportional to G. But then your period is also inversely proportional to what? The speed, right? The speed. Because something that takes a long time to complete has a low speed. That means that your speed is directly proportional to gravity. Right? And at the poles, you have, you know, the force of gravity is higher at the poles than at the equator. So if you take this up, then your speed also goes up. The correct answer is B. Question 30. Which of the following will reduce the frequency of a simple pendulum? Okay, so C is equal to 2 pi square root of L over G. All right, that's one of the formulas, which means that F is equal to 1 over 2 pi square root of G over L. So by just looking at it, you can see that F is proportional to what? 1 over L. All right, that means F is inversely proportional to L. That means that if I want to reduce the frequency, I should increase the length of the string. All right, increase the length of the string. That's option A. All right. Again, mass has nothing to do with simple pendulum. The frequency or the period of a simple pendulum, you don't see it in the formula. It's a mass spring system that doing this would actually alter, because that mass actually influences that. So we've come to the end of the video. Well done. and have a great day.